Explanation of the research paper, Safe and Adaptive Control of Non-Stationary Stochastic Systems via Lyapunov-constrained Distributional Reinforcement Learning. Overview and motivation. This research paper presents a novel framework called Lyapunov-guided distributional reinforcement learning with entropy regularization (LGDR-LER), designed to address one of the most critical challenges in modern autonomous systems, controlling systems that operate in constantly changing, uncertain environments while guaranteeing safety and stability. The authors identify a fundamental gap in existing approaches. Traditional reinforcement learning methods assume stationary environments where the rules don't change over time, but real-world systems such as robots, autonomous vehicles, and industrial controllers must adapt to changing dynamics, unexpected disturbances, and evolving safety requirements. When these systems fail, the consequences can be catastrophic, making safety guarantees essential. The three-part solution. The framework combines three complementary components, each addressing a specific challenge: 1. Distributional reinforcement learning uncertainty quantification. Traditional reinforcement learning focuses on expected average rewards, which can hide critical information about risk. For example, two different policies might have the same average reward, but one might produce wildly unpredictable outcomes while the other is consistent. LGDR-LER instead models the full distribution of possible returns using a technique called distributional reinforcement learning. This allows the system to understand not just what's the average outcome but what's the range of possible outcomes, and how likely is each one. This is crucial for making risk-aware decisions, especially near safety boundaries. 2. Lyapunov stability constraints safety enforcement. The framework uses Lyapunov functions, mathematical tools from control theory that serve as energy meters for the system. Think of a Lyapunov function like a measure of how far the system is from its target. It's always positive except at the target, where it's zero. The key insight is that the system is guaranteed to be safe if this energy consistently decreases over time. LGDR-LER enforces this by imposing a mathematical constraint that forces the policy to choose actions that reduce this Lyapunov function. This provides hard safety guarantees the system will never leave a predefined safe region. 3. Entropy regularization adaptive exploration. To adapt to changing environments, the framework adds an entropy bonus to its objective function. Entropy measures randomness or diversity in the policy's actions. By encouraging the policy to maintain some randomness, the system continues to explore new strategies even after learning a good policy. This is particularly important in non-stationary environments. A policy that was optimal yesterday might become suboptimal today as the environment changes. By maintaining exploration, the system can quickly discover new, better strategies when conditions shift. Why all three components are essential. The paper makes a compelling case that none of these components alone is sufficient. Through what they call ablation studies, removing one component at a time, the authors demonstrate, without distributional RL, the system cannot properly quantify uncertainty near safety boundaries, leading to risky decisions. Without Lyapunov constraints, the system cannot guarantee safety, potentially leading to catastrophic failures. Without entropy regularization, the system becomes stuck in suboptimal safe policies and cannot adapt to changes. Only when all three components work together does the framework achieve its full potential. Theoretical guarantees. The authors provide rigorous mathematical proofs that LGDR-LER delivers two key guarantees: asymptotic stability, the system will eventually converge to the target state, even as the environment changes. Finite time convergence, unlike many approaches that only guarantee convergence eventually, LGDR-LER provides an explicit upper bound on how long it will take to reach the target. This is crucial for safety-critical applications where you need to know when the system will be safe, not just whether. Empirical validation. The framework was tested on two highly challenging benchmark systems, one 3D Lorentz chaotic system. A classic chaotic system known for its butterfly effect extreme sensitivity to initial conditions. The system was modified to include time-varying parameters non-stationarity, random noise stochasticity, severe sudden disturbances at t equals 8s and t equals 12s. 4D hyperchaotic system. An even more complex system with multiple positive Lyapunov exponents, making it extremely difficult to control. Key results. The results demonstrate LGDR-LER's superiority across multiple metrics. Tracking accuracy, LGDR-LER achieved dramatically lower error metrics, i.e., 39.95, ISE, 95.48 compared to standard RLIE, 141.17, ISE, 1251.12, a reduction of over 70 to 90%. Safety compliance, only LGDR-LER achieved 100% safety compliance, 0 violations of the safe boundary, while all other methods repeatedly entered unsafe regions. Disturbance rejection, after sudden shocks, LGDR-LER recovered rapidly within 0.5 seconds, while other methods exhibited prolonged oscillations. Smooth control, despite its aggressive error suppression, LGDR-LER generated the smoothest control signals with minimal chattering. The ablation studies confirmed the synergistic necessity of all three components. Removing any component led to either safety violations or significantly degraded performance. Significance and implications. This research represents a significant advance in safe reinforcement learning, the subfield concerned with making AI systems that can learn while guaranteeing safety. The implications are far-reaching. Autonomous vehicles can adapt to changing road conditions while guaranteeing collision avoidance. Robotic surgery can adjust to patient movements while ensuring surgical precision. Industrial robotics can adapt to changing production conditions without risking damage or injury. Power grid management can respond to fluctuating demand while maintaining system stability. Limitations and future work. The authors honestly acknowledge several limitations. Computational cost. LGDR-LER requires 75% more training time and 183% more memory than standard RL. Hyperparameter sensitivity. The framework introduces several new parameters that require careful tuning. Scalability. While tested on 3D and 4D systems, scaling to very high-dimensional systems, e.g. 20+ joint robotic manipulators, remains an open challenge. Theoretical assumptions. The formal guarantees rely on assumptions that may not perfectly hold in practice, e.g. perfect Lyapunov function representation. Conclusion. LGDR-LER successfully bridges the gap between data-driven reinforcement learning and control theoretic safety guarantees. By combining distributional uncertainty quantification, Lyapunov-based safety enforcement, and entropy-regularized exploration, the framework achieves what no individual approach can: safe, stable, and adaptive control in changing environments. The strong theoretical guarantees and compelling empirical results position this as a significant contribution to the field of safe AI and autonomous systems.